Today's session is about Hungarian method. It is one of the methods to solve assignment problems, which is seen in operation research. An assignment problem is a particular case of transportation problem. The objective is to assign a number of resources to an equal number of activities, so as to minimize total cost or maximize total profit of allocation. The problem of assignment arises because available resources such as men, machines, etc. have varying degrees of efficiency for performing different activities. Therefore, cost, profit or loss of performing the different activities is different. Suppose that we have n jobs to be performed on m machines, one job to one machine. Our objective is to assign the jobs to the machines at the minimum cost or maximum profit, under the assumption that each machine can perform each job but with varying degree of efficiencies. Approach. First, check for balance, that is the number of rows is equal to number of columns. If not balanced, then it should be balanced before applying the algorithm. Step 1. Row reduction matrix. Subtract the smallest cost element of each row from all the elements in the row of the given cost matrix. See that each row contains at least one zero. Step 2. Column reduction matrix. Subtract the smallest cost element of each column from all the elements in the column of the resulting cost matrix obtained by step 1 and make sure each column contains at least one zero. Step 3. Assigning the zeros. Draw minimum number of horizontal and vertical lines, n, to cover all zeros. Examine each row. If number of 0 in the row is 1, then mark it and delete the corresponding column by drawing a vertical line, and if number of 0 in the row is maximum, that is more than 1, then skip. If all the zeros are not covered by the lines, then column examination is done. Examine each column. If number of 0 in the column is 1, then mark it and delete the corresponding row by drawing a horizontal line, and if no of 0 in the column is maximum, that is more than 1, then skip. Step 4. Apply optimal test. If each row and each column contain exactly one marked 0, then the current assignment is optimal. Minimum number of horizontal and vertical lines drawn, n, to cover all the zeros. If n is equal to n, where n is the order of the matrix, then an optimal solution can be made. If n less than n, then go to next step 5. Step 5. Modify the matrix. Determine the smallest uncovered elements x. Write uncovered value is equal to uncovered value minus x. Intersection value is equal to intersection value plus x. Line value, that is other value, are same. Step 6. Repeat steps 1, 2, 5 until an optimum assignment is obtained. Let's understand with an example. Solve the following assignment problem shown in table using Hungarian method. The matrix entries are processing time of each man in hours. Solution. In this matrix, these are jobs and these are men. First, check for balance, that is whether the number of rows is equal to number of columns. Here 5 jobs and 5 men. Problem is balanced. Matrix is of order n is equal to 5. Step 1. Subtract the smallest cost element of each row from all the elements in the row of the given cost matrix. See that each row contains at least one zero. Here smallest element in first row is 15, so 20 minus 15 is 5. 15 minus 15 is 0. 18 minus 15 is 3. 20 minus 15 is 5. 25 minus 15 is 10. Smallest element in second row is 12. 18 minus 12 is 6. 20 minus 12 is 8. 12 minus 12 is 0. 14 minus 12 is 2. 15 minus 12 is 3. Smallest element in third row is 21. 21 minus 21 is 0. 23 minus 21 is 2. 25 minus 21 is 4. 27 minus 21 is 6. 25 minus 21 is 4. Smallest element in fourth row is 17. 17 minus 17 is 0. 18 minus 17 is 1. 21 minus 17 is 4. 23 minus 17 is 6. 20 minus 17 is 3. Smallest element in fifth row is 16. 18 minus 16 is 0. 19 minus 16 is 3. 20 minus 16 is 4. Step 2. Subtract the smallest cost element of each column from all the elements in the column of the given cost matrix. See that each column contains at least one zero. Smallest element in first column is 0, so difference of the numbers is same. The smallest element in second column is 0, so difference of the numbers is same. The smallest element in third column is 0, so difference of the numbers is same. Smallest element in fourth column is 2, so difference of the numbers is 5 minus 2 is 3. 2 minus 2 is 0. 6 minus 2 is 4. 6 minus 2 is 4. 3 minus 2 is 1. Smallest element in fifth column is 3. 10 minus 3 is 7. 3 minus 3 is 0. 4 minus 3 is 1. 3 minus 3 is 0. 4 minus 3 is 1. Step 3. Assigning 0. Draw minimum number of horizontal and vertical lines, n, to cover all zeros. Examine each row. In this first row, one zero is present, so mark that zero and delete the corresponding column by drawing a vertical line. In the second row we see 3 zeros, so skip this row. In third row only 1 zero, so we mark it and delete that column by drawing a vertical line. Fourth row, 2 zeros, so we skip it. Fifth row only 1 zero, so we mark it and delete that column by drawing a vertical line. Now we see zeros uncovered by lines, so we start column scanning. First, second and third columns are deleted, so we start by fourth column. Here we see only 1 zero. So mark it and delete the corresponding row by drawing a horizontal line. In fifth column there are 2 zeros, but this zero is covered by line, so only this zero is left and hence we mark it and delete the corresponding row by drawing a horizontal line. Number of horizontal and vertical lines n covering all zeros are 5. Order of matrix n is also 5. When n is equal to n, optimal solution is possible. Where optimal assignment men and job is this, let's see it in the initial matrix given. 1 to 2, 2 to 4, 3 to 1, 4 to 5, 5 to 3. The optimal solution is equal to 15 plus 14 plus 21 plus 20 plus 16 equals 86 hours.